Welcome friends. Now this is third lecture on module 4. In this lecture we are going to talk about risk analysis example using a software. In the previous two lectures I showed you some of the important modules and some pull down menus on the software which is essentially used for risk analysis, which is FastRisk from DNV. This is third lecture in module 4 where we are talking about safety measures in design and operation on NPTEL course on HSC in offshore and petroleum engineering at IITM Madras. Let us quickly see what we will be seeing in this present lecture and how we will show you a very quick hands on experience on the software for a solved problem. We are going to talk about different failure cases and consequence analysis. The failure cases what we will discuss in this presentation will be dispersion, jet fire, BLEVE and fireball, and we will also do a consequence assessment, and ultimately we will end up in risk analysis or risk assessment based on the consequences what we identified for a given problem. The example considered in this study will be a LPG station located at XXX location in specific geographic location in the world. We all know that it is a common practice to carry out risk assessment for ensuring safe working practices. The current example study facilitates a better idea of hazard management, analysis of consequences, and of course the risk involved in the LPG filling station. This can assist the administrative authorities for legal sanction of new installations or expansion of the existing plants nearby that locality based on the safe hazard free zoning, which is one of the important visible outcome from this kind of example studies. The methodology followed to solve the problem will be following. We will first identify different or various hazards present in the station. Then for every hazard we will try to identify the consequences or the respective consequences of every hazard. Then ultimately we have got to feed in the different failure frequency based upon what are the identified consequences, and based on these two, frequency and consequences, we will land up in what we call risk analysis, which will become a two form output. One will be the societal risk and other will be the individual risk. Let us quickly see for our understanding what are those failure cases and consequences on a given LPG station which are generally considered in any such analysis. The failure cases can be a full bore or a failure of LPG outlet line which is arising from the bullets. We can also have what is called 20% cross sectional area failure of a LPG outlet line of the bullets. One can also envisage LPG pump discharge line full bore failure. It can be also a road tank failure, LPG pump mechanical seal failure, LPG pump outlet line gasket failure, or the road tanker unloading arm failure. Most of these failures are considered generally random in nature, and the consequences most commonly arise are jet fire, dispersion, VCE vapor cloud explosion, and BLEVE. In addition, one can also have LPG unloading vapor compressor outline full bore failure, catastrophic failure of a single bullet of a capacity 150,000 kg, and domino effects of series of bullets presented in the specific location. As we said, thermal radiation is one of the important input to be given depending upon the Pascal stability class. So various thermal radiation class are identified in the literature, varying from the intensity of that of 0.7 kilowatt per square meter to that of 37.5 kilowatt per square meter. The consequences or the types of damages that arise from these kind of radiation intensity are also shown in the figure, which is an extract from an IS code 15656 2006. Similarly, the second kind of damage could be overpressure, which arise from the blast overpressure indicated in bar, varying from 0.01 to 0.3, and the type of damages caused by variation of this blast overpressure is also shown in the table, and the casualty probability as advised and guided by the Indian code is also given in the last column of the table what you see in the screen. Now we wish to do a consequence assessment on these kinds of problems. So failure frequency becomes a very important input for such analysis using a software. Let us try to understand what are the possible failure frequencies which arise or may arise from a full bore failure, a 20% cross sectional area failure, LPG pump discharge, road tanker failure, LPG pump mechanical seal failure, LPG pump outlet line gasket failure, or road tanker unloading arm failure. One can ask a question interestingly, that how do we fix up these kind of failure frequencies? Of course, there are two methods by which these failure frequencies can be arrived at. One, look at the annual or biannual statistics of these kinds of failure which has occurred elsewhere on a similar plant in the world. Take a mean and try to relate this with that of the relevant Pascal stability class applied to the new location and comparable to the existing location where such accidents occurred. If they become comparable, then one can find an average value of this and say that is going to be my input failure frequency. Alternatively, one can also visit the plant, try to conduct what if survey, try to conduct hazard surveys and try to understand what would be the expected failure frequency of these kind of failure cases if at all the failure occur in the specific plant location for different Pascal stability class and different windward directions as given in the literature. So, based on such studies conducted, an example problem was arrived saying that serial number 1 to 7 have respective failure frequencies as I show in the right hand side of the column here, which is one of the important input to be given for the software analysis. Similarly, for LPG unloading vapor compression outline, catastrophic failure of single bullet and domino effects, these are again studied from the previous examples or previous experiences occurred from a similar industry elsewhere, and one can always feed them as an input failure frequency. Now, these are the results which has been obtained after analyzing this from the software, which I will show you now step by step procedure as we discussed in the last two lectures, but now I will run a video very quickly to have a hands on experience on this software, but let us quickly see what are the typical output I will generate from the software. For example, for a full bore failure of the pipeline, I would be able to compute the individual risk and societal risk in terms of average year, and they can be also plotted graphically. They can be also seen as the different sources where the failure could be concentrated and could be occurring. Similarly, one can also look at 20% catastrophic failure of the storage bullet, which can be seen as a radii envelope as you see from here as one of the important output graphically as well as in terms of FN curve for societal risk. So, societal risk in all the cases, for example, previous case also are given in terms of FN curve, which is frequency versus number of fatalities, whereas individual risk is again given in risk contour where the legend show different kinds of failure risk levels. For example, the red one here shows the contour of failure risk level of 1 10 power minus 6 per average year, and you are able to arrive at the catastrophic failure of the storage bullet for individual risk for the potential loss and societal risk based upon what you see from this table here for different modes of failure. For example, for road tank failure, for LPG pump discharge line failure, for LPG pump discharge line gasket failure, and for road tanker unloading arm failure, one is able to identify the societal and individual risk as an outcome from this software. Let us try to understand how this can be studied very easily using the software. Now, I will show you as an hands on experience. Once I get this, I will be able to simply compile them for two different plant locations, and I will know what are those individual and societal risk for different failure cases which we have already seen as one of the envisaged consequences of this specific problem. So, these are the results in terms of risk assessment done from the plant. Now, I compare this with acceptable level as given by Oil and Safety Industrial Directorate. In this example, we have compared the results with that of HSE UK for existing hazardous industries. Then I know what is the acceptable region, what is the alarm region, and what is the unacceptable region in terms of the risk value. If my risk number lies in any one of these regions of this triangle, then I will categorically qualify them as broadly acceptable or alarm region or unacceptable region. Now, I compared this and the table now shows the comparison. So, the table shows very clearly that the catastrophic failure of storage bullets at a specific plant location, both individual and societal fall on unacceptable range, whereas they fall on alarm region, whereas the remaining falls on the acceptable or broadly acceptable region. So, the study will lead to different kinds of variable outputs in terms of graphical and which shows societal and individual risks. Ultimately, they can be compiled and compared with an alarm triangle as applicable to oil and safety industrial directorate or any oil and gas industries. Then one can easily come to a conclusion whether the risk envisaged in a given plant is acceptable within the limits or not within the limits. So, now we will see how we can have an hands on experience of this software. So, friends, the first screen of the software will show you that we are operating on FastRISC 6.7. As seen from the previous slides, let us open a new file. Let us create run rows. So, let us select the raster image for a given material inventory, insert the image, select the image of the raster file from your computer as you see in the screen here, select any one specific image and select the coordinates. The coordinate system can be either the analysis offset from the coordinate system printed on the map images, or you can also convert them in terms of models to have a standard system printed on the map images itself. So, in this example we are trying to do the alternate way, and we have to give the local coordinates or local location of the origin as east and north coordinates as you see in the screen now. Once they are given, then you have to select a space for its projection and geographical area in the file, give the file name or the origin information, then identify the storage space in terms of coordinate system, where are the storage spaces available in the given plant. Once it is indicated, then give the geographic space, graphically select the area which is appearing on the right side of the screen now, select the area, then once you click it gives you the raster image of what you have selected in terms of coordinate system. Then you can show the important location where the material properties can be now identified, insert the mixture or the material. I am working out a new mixture in this specific case. So, once I click new mixture, I see on my left hand side a new mixture available and the material head. So, I click that, I go to the basis of adding them. My new mixture is having a specific combination of butane of a mole amount of 45%, and I also have the next possible chemical is propane, which is 55%. So, I add them and say it is general. I can always calculate the overall characteristics of this specific new mixture by simply saying calculate. You see here it is calculated. Now, the mixture data is being collected for internal mixing rules and overwrite any property data available to you, and therefore, it recalculates the value. You say yes, it recalculates and it will give you now the critical temperature, the critical pressure, the normal boiling point, the melting point, and whether the mixture is flammable or not, and what would be the equation of state applicable, and what would be the reactivity with the atmosphere. These are taken from the database of software. The moment you say calculate, automatically it does, and say OK, accept these values and say OK. Now, the new mixture has been predefined, and now you have got to define what we call the default weather conditions. Now, in this table on the left hand side you see these are FD nomenclatures are related to Pascal stability class, and of course, the number what you see adjacent to these legends are 1.5 meter per second, 5 meter per second, etc. And these are nothing but the wind speed available at the specific Pascal stability class associated with. So, you select the default weather, then you say OK. Now, select a specific Pascal stability class. Now, you see here on the cascade menu, pull down menu, you will see there are various stability class available varying from A, B, C, D. As you see, they can be even the moderate wind and windy night. So, all classes geographically of 24 hours period is covered in the specific sub menu. You click the moderate specific class, then also pick up the suitable substrate data and do this for the remaining stability class as well, and save the file and create a model. Now the study model has got different sources of failure or consequences, because I am actually doing a consequence analysis. You see here we are doing a consequence and risk analysis. So I want to create different sources like Jetfire, Fireball, down Baker-Stillo explosion, etc. Now for each one of them I want to specify the location. You can see here I can specify the location on the screen directly using a graphical raster image and associate that particular point with that of the any kind of feature of failure. So say select, then you can always adjust this by moving this using this particular menu, by moving this location to somewhere else if you are interested in. As in this case we have selected a point wrongly, now we are moving it towards some other location. So one can reassociate these points and do this for every kind of failure cases and associate the fuel related to this. We already defined the mixture, therefore the mixture is now available here. As you can see, a new mixture, the moment is a new mixture defined by me earlier in the material, the new mixture now has a category of specific composition of butane and propane. So I select that, and inventory mass participating should be given as an input in this case, as I said is 150 metric ton. The saturated liquid pressure is also given in terms of bar, which is an input for the analysis. So I must simply say what is my event frequency of this kind of failure. We are talking about vessel or pipe source failure. We have specified the material. Now we are talking about the risk, and in this risk column we are trying to give the event frequency, which is one of the important output, either given based on experience or based on existing data. So in this case we are entering 1.3 e power minus 5 and select the scenario. There are various scenarios available for a specific type of failure. So in this case, being a vessel or a pipe, I should look for either a line rupture or I can go for a leak. The moment I say leak, I must say it is a liquid phase to be released, and therefore I must say what is my hole diameter. Friends, please note, depending upon what you are selecting here, accordingly this menu and according to the data demanded will be in white, remaining all will remain in grey, which becomes inaccessible for you for a chosen data. That is a very interesting part in the software. So this guides you through and through how this can be easily done for a better understanding. So I have given hole diameter 50 millimeter. Now I want to also select what is my vessel head, because I am talking about vessel as well as pipe. Pipe I have given the diameter, whereas vessel I must also show what is the tank head, because depending upon this the volumetric discharge will be calculated. So I say 4 meter, and I must show what is my geometry, burn data, etc., which I already showed you in the previous presentation slides. So I now select horizontal, and now I also select what is my TNT equivalence and check out, and now I fix up this data for a specific vessel source and save it, and now run the analysis. The moment I say I have to run the analysis, since the data I prepared is not stored first, I have to store the data first, save it now on a specific file name. I say LPG2, save it, now I run, now it is running the value, calculating model for vessel pipe source for a default weather of Pascal stability class F, 1.5 meter per second wind speed. It will do for the remaining class also, you will see that. Now it is doing for D 5 meter per second and so on, D 1.5 meter per second. It has calculation for all, now the calculation is available. Now I can show the graphical output for all the three. You can see here for default weather, for LPG2 file, for a specific vessel pipe source run in the row 1 for consequence and risk analysis, I have got results for all Pascal stability class F 1.5 meter per second, D 5 meter per second and D 1.5 meter per second for all default weather data. Now I select all of them and show the graphical output, which is one of the typical output which I will get from this kind of analysis. You can see here the first output what I generate is actually the central line concentration versus distance. The run row is 1 as you see here, study folder is LPG2 which you remember here, and material what we use is new mixture, and flammability already we are given, and default weathers are what we have selected. Now one can see here where this is actually occurring in terms of concentration parts per million. So you can see here the yellow line corresponds to the concentration of ppm in downwind distance in terms of Pascal stability class 1.5 meter per second. The blue one what you see here which is overlaid and the green one which is also partially overlaid are for different stability class as you see from this result here. This is talking about the central line concentration. One can also see different output from here in terms of maximum concentration, the cross sectional failure, footprints etc., which I will show you subsequently. So, one can look at this, one can also look at the mapping. So, look at the mapping of this, select the source where you want to identify, say what is the possible jet fire arising from this, which gives me the plot now for different radiation. Now, we all know the radiation versus distance, we have selected the radiation level in terms of kilowatt per square meter. So, what is the radiation level we already know as we have an input from here. So, for different radiation levels for different Pascal stability class you will see that the failure scenario is being shown now for a specific stability class in terms of this. One can also look at the intensity radii from the selected source. You already selected a source where the vessel is located graphically. You know what is the windward direction that is given in blue, that is the input data, this is the windward direction, and this all becomes now downwind direction or what we call release direction. Now, we know what is the width of the specific radii intensity. Now, for a given intensity one can easily say the red line which you see here is actually a plot of Pascal stability class D for a wind velocity of 1.5 meter per second for a radiation of 35 kilowatt per square meter. One can plot this for different intensity. Of course, the example shown here on the screen now is plotting only for all the Pascal stability class, the radiation intensity is kept as 35 kilowatt per square meter. One can plot this for defined or user defined radiation intensities. So, intensity radii for the jet fire is now seen on the screen. One can also plot what we call lethality radii or the flash fire. For a given source selected in the screen, one can also look at the flash fire. Once I say flash fire, it shows me for different concentration. For example, the Kion one what you see here is the concentration of Pascal stability class D for a velocity of 1.5 meter per second which is occurring at a specific concentration, and the downward crosswind direction is shown here. This will be useful for you to plot the isopleths if you are interested in. So, one can see for different results as you see here as a flash fire for a specific vessel pipe source. Now, continuously one can look for saving of this file as a result. One can look at the different input data what we have given. You can see here what are input data we have given for this given problem. One can also look at the commentary which is generated from the software for use. FAST is being used here, unique audit number has been generated automatically for the given analysis. We have given already default weather and wind speed taken automatically because Pascal stability class and wind speed is 1.5 meter per second. Stability class is D, that is missing in this table anyway here. The dispersion results are given, that is a summary or the commentary what you have. The commentary runs in number of pages of 4. One can see all the data available in terms of how for different Pascal stability class the warning has been generated and the results have been produced. Once you do this for a vessel pipe source, then we are going for the next consequence failure which is a fireball. So, again the fireball I have to calculate the risk and I must say what is my file or what is my mixture for a fireball. I already have the new mixture available in my list. I pick up that and say OK. Then I must apply what we call the burst pressure as an input data, which is, if you understand, we are given 7 bar. Then event frequency is becoming one of the important input data which depends upon the experience or the mean data available for similar accidents occurred elsewhere in the industry. So, give this and try to compute the fireball shape. One can identify the released mass and give the mass correlation factor and vapor fraction of the mass. Then one can also calculate the contour data automatically and one will generate the value and run for the report and locate the source where a fireball is located and run the analysis. Once you run the analysis run for different Pascal stability class and you can see the results, select all of them and then now one can see the results for different stability class as you see from here. So, one can see interestingly the fireball is developed for different weather conditions the contours is generated, and that will tell you what is the societal risk and individual risk respectively. So, one can do it for the jet fire as well. So, new mixture is again selected, which is a given inventory of the material, give the elevation at which it is going to discharge, because you know jet fire discharge is very important for the plume and puff models we already saw in the last module of presentation. So, give the elevation, from there they have been released, what is the storage pressure in terms of bar, what is the temperature at release, and what is the hole diameter, which is 50 millimeter. Calculate now what are all the different values required. You can also give for a cone model what would be the angle of horizontal and the crosswind angle, or one can give a jet velocity, or one can estimate or calculate the jet velocity, give the radiation data as an input, calculate the geometry from the point, and then also do it for the Baker-Stolow explosion model. Select the mixture as a new mixture available in my literature as a standard data, give the flammable mass present in cloud as you see here, and also give the minimum and maximum distances of interest of your choice, where you want to look at what is the step size for analysis, because Baker-Stolow model is a numerical model which does this calculation for every step interval. So, select the step interval, select the material reactivity in terms of Mach number. One can also supply the Mach number if you know the Mach number for this calculation, and give the ground deflection factor, because you know interferences of physical presence in the ground will affect the plume and puff model as shown in Baker-Stolow explosion models. Select the geometry, it is a point source, and run the data for the given analysis. So, one can always say it is my new mixture and run the data and store the data for a specific location, as you see from here, for all default weathers as you pre-give in the problem. So, interestingly, now you see the contour has been generated for the default risk ranking point set as available from a given source. For different Pascal stability class. Now, one can calculate the risk, consequence and risk as analysis from this problem, compute the risk contours, click the risk contour, select the default ignition system or the ignition point where you want to ignite, select it from the graph, that is the ignition point selected, and one can always say what is my ignition probability and operating probability of that specific source of ignition, give that as an input data, and select the geometric point as specific elevation. Then one can also select different sources in terms of what is my ignition. There may be an electric line and what is the operating probability of that particular failure or ignition point. One can also select the default population set for a given problem, insert the data for the default population set, select the geometry and say that is my population set available, that is my population point, and the population can be given as an input data. In this case we are saying 2 and say OK. Then population set data can also be given as a rectangle, whereas an area or density of population is given in the input data. Select the area, draw a specific control line or a rectangle where you are giving the intensity of population. So, you are saying for this particular area the density of population is given as an input data, which is calculated and given as so and so for a given plant. So, enter the data and say OK, the population data is now given as a population rectangle, which you see here, which is hatched or filled. One can also give the population intensity for two sources. I can create two different intensities as you see in the screen here. Earlier was 50, the present is also 50. I can create two different intensities. Then calculate the risk ranking point where I want to calculate the risk, select it from graphic point. So, select that as a point of elevation selected from the geometry automatically. Also now calculate the plate boundary, plant boundary set which you want to analyze, that is very important. As I said, it is generally done segment wise. So, we go for a plant boundary as you see selected from the screen now, and that is my plant boundary. Once I select the plant boundary, then I show the plant boundary becomes blue in this case after selection, then I go for the weather data, then I run the rows for analysis. I have selected only one row for the analysis. Now you can see here, now the first row of analysis for consequence has vessel and pipe source, fireball, jet fire, Becker-Strillo explosion model, all are predefined, all weather data are predefined. We are now going to do for run all select rows for calculation, select all of them, estimate the consequence and risk as well for all of them, then also give the different factors for analysis, which is seen from the screen now. For different run rows I am giving 1, it means all of them could occur simultaneously or subsequently. Run the analysis, percentage of progress for running is shown, it is doing calculation for every weather window and every Pascal stability class for different wind speed, for different failure analysis. Now you view risk contours, select this particular button for viewing risk contour, then select that button. Now you are viewing the risk contours for different failure modes as you see here. This is my risk contour because that is my source, that is my population rectangle as you see here, 2 rectangles, one here and one here for different intensity. We also given a specific population concentration. Now the risk level in terms of what is the risk available average per year in terms of risk density or contour is plotted. For example, the orange one shows the risk level is 1 10⁻⁻⁶ per average year and so on and so forth. So this becomes an output of the software. Then you try to magnify this and see the differences or understanding. You magnify this and show where is my source and where is my risk level, where is my risk contour, etc. One can also generate a report for different run rows. One can see a graphical output which will give me a societal risk now. For example, for maximum risk criteria which we have specified in the problem, minimum risk criteria is also specified in the problem. For an FN curve which gives me the societal risk is also now plotted, which can be seen, and the combination problem is now the risk level is somewhere here which is much lower than the minimum one for a specific combination of run row 1. So again select for different sources, for different ignition points, select it for any other point available of choice. For example, let us say define the population set, change the population set now, insert a new population set or edit the existing population set. For a run row 1, now you are giving a new population dimension, you are taking the population closer to the source as you see from the screen here. So I call this as population rectangle 2, I am giving population, earlier I gave 50, now I gave 50, but I moved the population concentration to the specific source and the source now category is industrial. Now I rerun the analysis, you will see that the acceptable risk level will now change. So I have to follow the same procedure, giving the factor as 1, I am calculating risk for default population 2 for industrial type, I run the analysis, show for the graphical output, risk contours, graphical output. Now you see here interestingly the earlier accept combination line was somewhere down here 1�7, 10⁻⁻⁷, now it has moved up closer to the minimum risk value. As the population intensity move towards the point of source, you will obviously see the risk on the society is much higher. So the software gives you a very visual and graphical output in terms of better understanding as you see for the specific problem. One can also see the risk contours plotted, and the risk contours can be available in terms of individual risk contours available here, and now you can see also the orange one has got now changed 1 10⁻⁶ average year, it has moved to the point where the population density is being now focused. So it gives you both societal and individual risk in terms of graphical output, and that is the point of interest. So it is a fast risk software which has been demonstrated for you for your problem. So interestingly, ladies and gentlemen, we have understood that how the problem can be solved using a standard software which gives you an hands-on experience, a better understanding. We picked up a specific example, defined the consequences, also understood how to give input frequency of failure for each one of them, identified the risk estimated from the software, elaborated them in terms of individual societal risk which can available as a graphical contour or a graphical plot. So these kind of software experience will help you to understand physically, visually, virtually how a risk analysis can be understood very easily and first hand experience can be achieved. Thank you very much.